Okay. Can I get everyone's attention? Thank you. This was the last exercise we looked at yesterday, and we answered all the questions. This was our answers in example number 2. There is one repetition of values, so even though the interval from 0 to 4 has 5 elements, what is defined in this set is only 4 elements. And indeed, for this example, we had said that the input, so to speak, is all natural numbers, but the output that we get from the specification is only the two numbers +1 and -1. That also answers this question, what are these two elements? There are only two elements in this implicitly defined set. Just one quick remark, which you can immediately forget after I made it, but I want to make it nonetheless. As computer scientists, we are not really dealing with the foundations of mathematics. Mathematicians would, when they want to introduce real numbers, do it in this more involved and complicated manner, as is said here. Sometimes mathematicians would even define natural numbers with a pure logical axiomatization, where they say the number 0 corresponds to the empty set. Any number n plus 1 corresponds to whatever n corresponds to. At the beginning, the empty set, union the set that contains n. And by the way, this is a notation that I will be using throughout the course. And this is said here. If I want to emphasize that an object, an expression, or a formula is defined through an equality, then I will use this symbol here for defined. It denotes that the left-hand side is used as an abbreviation for what is defined or what is given on the right-hand side. This, just as a side remark, we won't be going into these details as computer scientists. We are satisfied with the more informal introduction into both integers as well as real numbers. What is said here should have become clear with everything that I said yesterday. When we look at the sets of numbers, then we do have this relation. The set of positive integers is a strict subset of the set of natural numbers. Why is that? Because this is almost the same, but it contains the number 0 in addition. Then we've got the integers, which contain all negative numbers in addition to the natural numbers. The rational numbers, which contain all positive and negative fractions, but not irrational numbers. They are contained in this set. Now, sometimes, and I think I've already introduced this notation here, sometimes we define derived sets of numbers, for example, positive natural numbers with that small greater 0. Also, small greater 0 for the integers would mean all the positive integers. This is all n's that are greater or equal to 1. And we can do the same with rational numbers. This would be all strictly positive rational numbers, and this would be all strictly positive real numbers. Sometimes this notation is being used as a shorthand for the right-hand side. 2 times z corresponds to all, you can say, even integers, because it is defined as all the elements 2 times x, where x is an element of z. And this is a very short form of writing down that you mean all the multiples, positive and negative, of 2. And you can even say something like this. This would be all integers that are obtained by this definition, 3 times x plus 1. We have already seen intervals. They can be applied to both natural numbers as well as real numbers, and of course all the numbers in between. These square brackets, as I've introduced them, means all the numbers between a and b, including both a and b. Whereas if I use these round parentheses, and this is really standard notation, then I mean the interval between a and b without the boundaries. That is all x that are strictly greater than a and strictly smaller than b. Then sometimes you can mix this notation For example, if you use this bracket here, it means include the A. Parenthesis here, it means exclude the B. And therefore, this interval will be a subset of this interval, but not necessarily the same. And we have that you can also have the open interval here for A and closed for B. And then this interval that doesn't contain both A and B would again be a subset of this interval. You would see that when we apply this to boundary cases, the interval from A to A that should not include the boundaries would be the same as this one and the same as this one, because in all cases you exclude the A. That would be the empty set, whereas if you use two brackets, then this would contain exactly one element, namely A. Intervals of positive integers, natural numbers, and all integers will always be finite. If m is smaller or equal to n, then we know that the number of elements in here is contains all the numbers from m to n, and therefore it's n minus m plus 1. I've already said that last week also. This is only true for integers, but not for rational numbers and real numbers. For rational numbers and real numbers, if m is strictly smaller than n, then you have infinitely many elements in any interval. Quick check whether we understand this notation. How many elements do we have in this set? 2. And how many elements in this set? 3, yes. So this is the interval from -1 to 1, and it includes 0. The answer, however, is only correct if you interpret this interval over the integers. If you interpret this over the real numbers, the answer would be infinite. Now, it's a bit tricky that this hasn't been said here. Sometimes it becomes clear from the context whether we are talking about integers or real numbers. Better still would be to always say whether this should be interpreted over the integers or the real numbers. And if we interpret this interval over integers, how many elements? 1. It would only be the 0 because -1 and 1 is not included. And clearly in here we've got 3 elements. This would actually be the same as this interval over integers. All right, so this is not too difficult. Again, just keep in mind that it may depend on what underlying set you're talking about, whether you have a finite number of elements or an infinite number of elements in this interval. Now let's get back to set operations. I briefly hinted at these yesterday already. Now in a bit more detail, the simplest and most standard set operations would be union, where you take any element that is in A or in B, so you take all elements in A and B together, versus the intersection, and this would be the standard mathematical notation for that. You take only elements that occur in both A and B. Now, the way I've said this, you might already see that there is a correspondence between these set operations and logical operations, like contains all elements that are in A or in B, contains all elements that are in A and in B. Now, this correspondence will be discussed next week when we dig a little deeper into this basic form of logic. The explanation for this is that you can match a set A with the subset of the universal domain. If you're talking, for example, about numbers and you define set A as the even numbers, where a property, let's call it lowercase a, holds, such as being divisible by 2. And you can match a set B with the subset where B holds. For example, you can say all the numbers that are greater or equal to 0. And then if you define the union of A and B, this would correspond to the logic condition that A has to be satisfied or B has to be satisfied. That is, in my example, the number has to be even or it has to be greater or equal to 0. And conjunction and, the same as intersection, of two sets would mean that the number has to be even and it has to be greater or equal to 0. We also say this is a standard term that two sets A and B are disjoint if they don't have any element in common. That is, if their intersection is the empty set. Some very simple properties of union and intersection is if you know that the union of A and B is B, then you know that A must be a subset of B. Why is that the case? If there was an element in A that is not in B, then when you construct the union of A and B, there would have to be that one element that is in A and not in B, and therefore it can't be the same as B. So from this, we can conclude that A must be a subset of B, and it also holds the other way around. This, by the way, is the standard mathematical symbol for an if and only if. And again, we will be looking at this more closely either at the end of today's lecture or at the beginning of next week's lecture. When we look at logic, intuitively it means that this condition is true if and only if this condition is true. And we have a symmetric condition for the intersection. If we know that the intersection of two sets equals one of the sets, then we know that that one set must be a subset of the first set. That is, by intersecting with A, you don't lose any elements, and that means that any element in B must also be in A. Otherwise, you would be, so to speak, losing this element. Other very common set operations would be the set difference, where you take all the elements that are in A, but not in B. Sometimes also known as the relative complement. It does correspond to, logically speaking, satisfying the property A, and at the same time not satisfying the property B. So if you take the set of, let's say, even numbers, and you subtract from this the set of positive, when I say numbers, in this case I mean integers, the set of positive integers, you will be left with all the negative even integers. This is maybe less common and might be a symbol that you haven't seen before. It stands for the symmetric difference. Either an element is in A and not in B, or an element is in B but not in A. And it is defined as precisely what I said, A without B plus B without A. And also that has a correspondence to a logical operator of the underlying condition. It corresponds to A and not B, or B and not A. Or in other words, A if and only if not B, which is also known as exclusive OR, which we computer scientists like to abbreviate by XOR. And again, we will be talking about this in more detail when we get to the underlying logic of statements like this. Finally, we can build the complement of a set, that is all the elements that are not in a set A. And that typically really only makes sense when you're talking about a universe around this set A. Because if it can be anything, then this complement would just contain any possible object that you could possibly think of. So the complement would always have to be defined with respect to a given universe. For example, if you take the integers as your universe and you have a set A, the even integers, then what the complement would be is very clear. It would be all the odd integers, all the elements that do not satisfy the property that defines the set A. This is often a very nice way of visualizing some of the set operations. If you want to read more about this, then do have a look at these pages 23 to 26 in the textbook, where this is described in more detail and with more examples. The so-called Venn diagrams are a simple graphical tool where you illustrate every set that you want to talk about by a circle that intersects with other circles, and it typically makes sense with two sets or with three sets. If you have more than free sets, then this is not really very handy, but lots of simple properties of sets suffice for those. It suffices to have 3 sets, and then you can mark every region in a diagram like this corresponding to a particular set operation with regard to these 3 sets. For example, this region here would contain all elements that are in A and in C. In other words, this denotes the intersection of A and C, and this contains all A and B and C. Now you have to be a bit careful with reading this, because actually A intersected with C is this whole area here. All the elements that are in this circle and all the elements that are in this circle. Just to give you a simple example, here I've got all the numbers between 1 and 20. This is my universe. And then I've got 2 sets. This set is defined as containing all the odd numbers from 1 to 19. This contains all the numbers greater than 10 in this universe of all the numbers from 1 to 20. And then clearly there are some numbers that satisfy both properties. They are both odd as well as greater than 10. And we've got a few elements that are outside these 2 sets. All the numbers that are not odd, that is even, and that are also not greater than 10, that is, which are smaller or equal to 10. And then with this simple example, you can look at, for instance, what would be B union the complement of A. It would be all the elements in B and all the elements that are not in A. So not these elements, but it would be these elements and those. So some of these questions, when you want to calculate some of these operations on sets, can be easily answered with the help of diagrams like this. These can also help, these diagrams, to understand basic laws of set operations. They are listed here together with their standard name. I'm not expecting you to memorize all these names, but you will frequently see names like this reoccurring with other laws, and this is why I'm mentioning them here. Commutativity usually means that you can swap the order in which you apply an operation to arguments. And clearly, if you construct the union of 2 sets, all elements in A plus all elements in B will be exactly the same as taking all elements in B together with all elements in A. Associativity typically has this form. Distribution is a law that applies to these set operations. It says that A union the intersection of B and C is the same as, first of all, taking the union of A and B and then intersecting this with the union of A and C. You might be very familiar with this law if you have dealt with set operations like this before. If not, then it can be really helpful to draw a Venn diagram to understand why, for example, an equation like this is true. And I'll just illustrate this with, let's say, this particular example with the distribution. We've got 3 sets. Let this be A, B, and C. And now the question was distribution. We want to verify that A union the intersection of B and C is the same as another expression. So let's first of all determine the intersection of B and C, as we have in this law here, B and C. This is set B, this is set C, so the intersection of B and C would be this area. I hope we can, it's not too bad, can see it. And then union A, so we have to take this together with all the elements that are in A. So A union intersection B and C would be exactly these 2 areas together. Now we want to check whether this is really the same as, according to what the law claims. taking the intersection of two sets, namely the union of A and B and the union of A and C. Now, if we look at the union of A and B, this would be everything that we have in here, union A and B. And the union of A and C would be everything that we have in here and in here. Now, this is a bit more difficult to see. Now we have to intersect the two colored areas. That is, we have to take all the elements that are colored both in red and green with the two colors. And you can see that this would be everything in here. This is both red and green, and also everything in here. So we would obtain this. And if you now compare this to what we have here, we do actually see that it is indeed the case that if we take A and combine it with all elements in B and C, this was this area, this was this area, then this is indeed the same as A union B and A union C. Now, this is one way of providing visualization of a proof of basic law for these set operations. And it might be a good idea for you, if you're not familiar with these laws, to try this with the other distribution law, to try this also with some of these laws, and possibly also look at the so-called De Morgan laws, which say that the complement of everything that is in A and B is the same as everything that is not in A intersected with everything that is not in B, and also intersected and union exchanged. Now, a quick summary of these set operations as exercises. Suppose we have a set that I'm here calling capital sigma, the Greek letter sigma. There's a specific reason why I'm calling it sigma, which will become clear in just a few slides from now. But for the moment, assume that this is just a set that contains the two letters A and B. How many subsets do we have of this set? 4. It would be 4. We would start with the empty subset, then the singleton sets that only contain A and only contain B, and then the set itself would be A and B. How many proper subsets do we have? Proper subsets would be only 3, yes, because the last one, A and B itself, is not a proper subset. So the size of the power set of sigma is? Size of the power set is? 4. Yes, it is 4. It is power set is all the subsets in sigma, and therefore the size would indeed be 4. Maybe that was too simple, that question. Let's have a look at this exercise. The symmetric difference of A and A, even if we are not given A. Can we say something about this? A complement? No, this is not correct. Empty set. Yes, it's the empty set. We have to take all elements that are in A together with all and that are not in A. So you can have an element in here only if it's in A and at the same time not in A, or it is not in A and in A. So we've got something that is logically inconsistent. We can't have an element that is in A and at the same time not in A. No matter in which order we apply this, just remember how the symmetric difference was defined. If you replace this B by A, then A without A is the empty set. A without A is the empty set. Empty set union empty set is empty set. So it would contain no element. And what about A and symmetric difference with the empty set? That would be A itself. Yes, this is correct. All the elements that are in A and not in the empty set. And of course, no element is in the empty set, so everything in A would satisfy this. This will always be A. There's this other exercise that asks you to relate the cardinalities, whether you can say something about what is the size of the intersection or the size of the union in terms of the size of the intersection and the size of the sets themselves, and also asks you to do that with the difference and symmetric difference. I will just show you the answer here. What we can say, and this is true for all sets A and B, is the union always contains all the elements in A and all the elements in B. So if you count them, you would count the elements in A and the elements in B, but you have to make sure that you don't count elements in the intersection twice, and this is why you have to subtract the intersection, the size of the intersection once. This becomes very clear when you look at an example like this. If you want to count the number of numbers that are in A or B, then you count the elements in here, you count the elements in here, but you would have counted these elements twice, so you would have to subtract them in order to get the number right. And similar laws apply to the set difference. A without B, the size is A minus the intersection of A and B. Symmetric difference, you can only take elements that are in A but not in B, and only take elements that are in B but not in A. So you have to actually subtract the intersection, the size of the intersection, twice. And again, this will be very clear if you look at this example. If you only want these numbers and you only want to have these numbers, then when you add up the size here and the size here, you would have counted this twice, and you don't want to have these numbers at all, so you have to subtract them twice. Last comment, if you look at this equation, then you can see that if you take the union of two sets and you add the size of the intersection, then this is exactly the sum of the sizes of these two individual sets. Now, the last concept that I'm going to introduce in terms of operations with sets, we will use that later for several purposes, is the so-called Cartesian product, the notation for which uses this cross. And it is meant to say that you might have two sets, say S and T, and you want to build all pairs, denoted again by these parentheses, not meaning an interval, but meaning pairs of elements, one from S and one from T. Do note that this is an ordered pair, so S and T may not be the same or is not the same as the pair T, S. If you wish, you can view this as a vector with two elements. The first element comes from S, and the second element comes from T. And of course, S and T could be the same, so you can easily talk about pairs of numbers. And then one pair of number would be 3, 4. Another pair of numbers would be 4, 3. We can extend this, and this would be the standard notation to say that you have not pairs of elements, but you've got vectors of size n, or n tuples, as we sometimes like to say, where every individual element comes from a specific set. So if you've got 3 elements and you construct the so-called Cartesian product, or sometimes also called the cross product, simply because of this symbol, then it would be all possible combinations of values from every individual set. For instance, you can say you build triples, where the first 2 elements are integers and the third element is a real number. And then one possible triple or vector would be 2, 3, pi. But what would not be possible is to say 2, pi, 3, because I've said the first 2 elements must be integers and only the third element can be a real number. Often we want to have, and this is probably what you're more familiar with when you talk about vectors, that all the elements come from the same underlying set. So we can talk about 3-dimensional vectors over real numbers, for instance. And this would then be the real numbers to the power of 3, which corresponds to the cross product, real number cross real number cross real number, or Cartesian product of real numbers. And this would be all 3-dimensional vectors with real numbers. And s to the power of n, you would just take the cross product of n for an arbitrary number n of elements. When we apply this definition to a boundary case, you would see that the cross product or the Cartesian product of empty set plus an arbitrary set will always be the empty set. And this is important to understand why this is the case. When we construct the Cartesian product, we are required to take an element from the first set and combine it with an element from the second set. Now, if we don't have a single element in here, we can't combine any element from the first set with an arbitrary element from the second set. So there is no way in which we can come up with even a single pair of this form, and this is why this has to be empty. It contains no element. This is a boundary case that, of course, in practice you wouldn't apply, but it's something that you would have to understand if you see a formal definition like this and you want to, for example, prove a property that is universal and applies to all S and T, including the empty set, then this would be a boundary case to take into account. Now, how many elements do we have in the Cartesian product of two finite sets, S and T? The answer is quite simple. You would multiply the size of S with the size of T. And why is that so? Suppose we have one set with 3 elements and we have a second set with 4 elements. Then you've got 3 choices for the first element in a vector and 4 choices for an element for the second element in the vector. That gives you a total of 3 times 4 possible choices. And therefore, there are 12 vectors that you can construct with these 2 sets. In general, we can say the Cartesian product or the cross product of n sets will always, when you look at how many numbers we've got or how many elements we've got, will always be the product of the individual sizes of this set. And in case you haven't seen this symbol before, this capital Pi stands for the product of individual elements. You might be more familiar with something like this. I equals 1 to n of I. This would be the sum of all elements from 1 to n. So this is defined as 1 plus 2 plus n. This is the sum, and this big pi does the same thing but with multiplication. So if we multiply all the numbers from 1 to n, I, then this would be 1 times 2 times 3 times n. Which, by the way, is defined as what? Does anyone know how the product of all numbers from 1 to n is called? Factorial, yes. So this is the factorial of n, and the standard notation for this would be this. We will see that much later when we will be looking at combinatorics and counting, but the main purpose of this was just to illustrate this symbol pi here, which stands for product. And in our case here, it means that you take the individual sizes of the sets from which a vector comes from, or from which a vector comes. Now, last thing before we move on to another topic which you might be less familiar with, we will be using functions. Functions mostly will be defined or are defined in computer science as a set theoretic concept, by which we mean that when we talk about a function, we say that a function maps elements from one set to elements from another set. The standard notation that I will be using is for a function f to map elements from S to T, illustrated with this long right arrow. It describes pairing of the sets, and it means that F assigns to every element from S a unique element from T. We've seen a couple of functions already, for instance, the floor and the ceiling. The floor and the ceiling were defined as taking any real number, so S, in this case, was the set of real numbers, to an integer. So in this case, T would be the set of integers, floor and ceiling. And we also had absolute value, and absolute value would be defined as taking a real number and mapping it to a real number. Sometimes when I want to emphasize that a specific element is being sent or used as input, then I would be writing it in this form, a slightly different arrow, indicating that I mean that a very specific element X is mapped to a specific element Y, which then means the same as the function value of X is Y. So if we take the floor function, then I might say that the floor function has the property that it maps 3.5 to 3. And then I would use this arrow when I talk about one specific element, whereas when I talk about the general, as we sometimes call it, signature of this function, I would say it maps integers, or rather real numbers, to integers. Now let's briefly introduce a topic that you might be less familiar with, because this is really important and relatively specific to computer science, namely the concept of formal languages. And I've got only 2 or 3 slides on this. We will define a few formal languages in this course, and you will find formal languages also almost everywhere else in computer science. Especially any programming language has a formal definition as a formal language, which tells you what is an allowed expression in this language and what would be syntactically incorrect. The basics for formal languages is that you've got an alphabet, a so-called alphabet, and for alphabets in formal languages we invariably use capital Greek letters. It also now explains why in that particular example we had that capital sigma for these 2 letters A and B. An alphabet for a formal language is a finite, non-empty set. And here are a few examples. You can take the 26 letters that are being used, for example, in English. For single words, if we assume that we only use lowercase letters, then we do have exactly 26. Now, this would be a very common alphabet, one that you are very familiar with. We could construct an alphabet like this, where we say, first of all, we have the minus symbol. Then we've got the letters A to Z. And we could also use spaces in our language. Note that if we have only letters, then we can build only single words, but we can't have 2 words with a space in between. But if we add spaces, then we can construct this alphabet, and what would be possible expressions in this alphabet? We could, for example, say A space B, or we could say minus A minus B space Z, and so on. A very useful alphabet for computer scientists is this probably smallest alphabet that makes sense, where you have got only 2 elements. By definition, you can also have an alphabet with only 1 element, but with only 1 element, you're really very restricted and can't do a lot. But with 2 elements, as we all know, we can represent, for example, all integers, positive and negative, with the help of this binary notation. We only need 0s and 1s. And we computer scientists, we use this alphabet a lot. We use this not only to encode numbers, we use this to encode words, sentences, texts. We use this to encode images. We use this to encode videos. And everything that can be represented and stored on a computer can be ultimately represented with this simple alphabet of just 0s and 1s. And of course, you need lots of 0s and lots of 1s for any meaningful application. This is an alphabet that you're very familiar with for decimal integers. 0, 1, up to 9. I should have been more precise. This is actually for positive integers, because with just 0 up to 9, you cannot represent negative integers. For negative integers, you would want to have this minus symbol in addition. And unlike with binary, this binary alphabet, where you could say that every combination of zeros and ones can be understood as a binary number, we would not normally say that every combination here corresponds to the proper representation of a decimal. You wouldn't say 0099 is correct. If we want to say 99, then we wouldn't have the leading zeros. So sometimes you can have expressions that can be represented in the alphabet that you would classify as syntactically improper. In a similar way, you can understand the dictionary of the English language, assuming that we have only lowercase letters, as all combinations of letters which correspond to actual words. And then lots of combinations don't correspond to existing words, and lots of other combinations do correspond to existing words. Do note that the cases that I'm giving here all have a natural ordering. We know what the alphabetical ordering is. A comes before B, which in turn comes before C. Same for these numbers, but alphabets don't require this. And you can, for example, use all Chinese characters together, which are not ordered, don't have a natural order. And as long as this is finite, you again officially have an alphabet. And you can take these characters and combine them together to form either meaningful or not meaningful sentences. Here are the basic definitions for what we can do with alphabets. We can construct so-called words, and the word by definition would be any finite string of symbols from an underlying alphabet. We have, and this is very typical for mathematicians and also computer scientists, we have to deal with boundary cases, and we have the concept of an empty word, which sounds a bit funny because this is not normally something that you would use, but it comes in very handy when we talk about formal languages. Empty word means an empty string. That is, we don't even take a single letter or element from sigma. The standard notation for the empty word is this lowercase Greek letter lambda. Here are examples. If we take the 26 letters for the English alphabet, A, B, and A would be a word that we can build if we have the binary digits, only zeros and ones. Then we can take long combinations of zeros and ones, etc. The length is a function that maps every word to a natural number. The length of a word is defined straightforwardly as the number of symbols in the word, so that the length of ABA or the length of AAA is obviously 3, and the length of lambda, because it doesn't contain a single element, is 0. We can do lots of interesting things with words when we combine them. The only operation on words that we are interested in this course is concatenation. And concatenation is written as just gluing together individual words. So when we have two words V and W, by VW we mean the first word immediately followed by the second word. And clearly, if both words come from the same alphabet, then gluing them together will also give you a word from this alphabet. It might not be a syntactically correct word if you have an underlying definition of what you think is correct and what is not correct, but it will be defined as a word. We can construct this, word W followed by word V followed by W, or we can say take a particular word W and add this to the two letters A and B, and so on and so forth. From this you will immediately see that when you glue the empty word in front of a word W, then because there's nothing in the empty word, this will just give you the word itself, and this will be the same as adding, so to speak, the empty word at the end of W. It doesn't add anything. It's like the empty string that is added to a string, and the result will just be the string itself. This all nicely fits with the definition of length. The length of the combination of V and W is always the number of elements in V plus the number of elements in W. And you can see that because there are 0 elements in here, this is also satisfied for these special cases with the lambda. Now, one more slide on basic notations for alphabets and words. When we want to say that we are particularly interested in all words over a particular alphabet sigma of a specific length, let's say k, then we would, or we will be writing it in this way. For example, if you have binary numbers, then sigma would be 0, 1, and you want to look at all vectors of 4 digits, then k would be 4. So the set 0, 1 to the power of 4 would be all 4 bits that you can express, starting from 0, 0, 0, 0 to all 4 bits are 1. Now, sigma to the power of 0 would not be the empty set according to this definition. It would be all words of length 0, and there is one word of length 0, namely the empty set. Sigma to the power of 1 would be the same as sigma. All words of length 1 is, of course, just all the elements that we have in our set. Then the notation sigma star is also very common to indicate the set of all words that you can possibly construct from sigma. And sigma plus will be almost the same as sigma star, except that it doesn't contain the empty word. So it contains the set of all non-empty words of any positive length. They can be arbitrarily long. They have to be finite, but they can be arbitrarily long. Now, if you combine these definitions, you will see that sigma star is defined as the empty word plus all the words of length 1 plus all the words of length 2 plus and so on and so forth. Sigma star contains all words, and therefore it contains all words of a specific length. Last notation is when we want to say that we are interested in all words up to a particular length. That is, for example, all bit strings up to length 4. Then this is a standard notation. Smaller or equal to 4 would be all words of length 0, all words of length 1, and so on, up to the maximum length that we want to allow, in this case, 4. And this big union here obviously just abbreviates these individual union operations here, where we take all these sets together. And then you can see that sigma plus would be all elements, all words, rather, of length 1, plus all the words of length 2, and so on, but not the empty word, and therefore this is the same as sigma star without lambda. That already concludes the introduction to that basic concept of alphabets and words that we can construct over alphabets. Let me just add that when we then talk about an actual formal language, which we will do later in different contexts, then in formal language theory, a language is defined as a subset of all possible words that you can construct. And in a sense, this is even true for English. English as a language allows you to construct certain words and certain sentences which are syntactically correct, and other combinations of letters would not be syntactically correct. This is particularly true when we talk about a formal language, like a programming language. Python or C or any other programming language would also be defined formally over an alphabet. What are the symbols that you can type, and what is a subset of these combinations of symbols that makes sense, that could be understood by a compiler. So typically only those subsets of sigma star that can be formed according to certain rules, which we also call grammar, like we do in English when we talk about grammar. We also say grammar for formal languages. According to certain rules, when we use them and we form certain words, then these words would correspond or be included in that language, and these would be the ones that we accept. Like a compiler would accept one program and reject another program because it's syntactically incorrect. So I've already said that this would be called grammar. If we have a collection of these descriptive or formative rules, and examples is not only natural languages like English, but in particular programming languages or database query languages. Now, just to show you one example, and again, I'm referring to a particular programming language, Python. Again, assuming that many of you will be learning Python in parallel to this course. If you look at the formal definition of what is allowed syntax in Python, then you might come across something like this, which defines formally what you are allowed to use as an identifier. I'm assuming that Eric is only informally explaining this, but a proper manual for a programming language like Python would include something like this, which tells you exactly what is an allowed identifier and what is not allowed. And interestingly enough, you will see some of the notation that we have just introduced, in particular this star symbol. Now, what does it mean when we define an identifier for Python? It tells you that you are allowed to use a letter, and letter is defined as either lowercase or, this is a symbol that can be understood as a union, is either a lowercase letter or an uppercase letter. Lowercase is defined as A to Z, and uppercase is defined as capital A to capital Z. Or you start your identifier with an underscore. So if you see this, then you immediately know that an identifier cannot start with a number, for example. You have to use a letter or an underscore. This has to be present in every identifier, so you can't have the empty word as an identifier, and clearly that doesn't make sense in a Python program. And then this letter or underscore can be followed by letter, digit, or another underscore as many times as you wish. And this is what this star here stands for. It says that any combination of letter, digit, and underscore can be used, including 0. So you can have an identifier which consists only of a letter A to Z, or even only underscore. This would be allowed in Python, although probably not very recommendable, not very recommended, but syntactically possible, followed by any number of these. Sometimes you might see other definitions where this star is replaced by a plus, and you know how to interpret this now. It means that you are required to have at least one element, possibly more elements of this underlying definition. So this just to give you a brief illustration of why these symbols that I've introduced here are really important for computer science, and where you can see them when you talk about formal languages such as programming languages, which is given here as one example. To complete this, and then probably to have a break for today's lecture, let's have a look at these exercises here. I've just straightforwardly giving the solution just to show you more examples. If sigma is this set ABC, then sigma star is the set of all words that you can build over sigma that is from letters ABC. The size of this set is infinite because you haven't restricted the length at all. Whereas if we say that we only want to consider words from sigma star that have a length small or equal to 4, where again sigma is ABC, then you have to consider all words of length 0, which is only 1, all words of length 1, and there's exactly 3 words you can build, all words of length 2, of which you have 3 by 3, that is 9 possibilities, because you start with AA, then AB, AC, and so on and so forth, up to CC. That would be 3 to the power of 2, up to length 4. And we've got exactly 3 to the power of 4 words of length 4. If you want to calculate the sum, then there is a nice, easy formula that you may or may not have seen in high school, for example. It's not something that I expect you to know, but it might come in handy when you want to calculate sums like this. The sum 3 to the power of 0 up to 3 to the power of 4 is the same as 3 to the power of 5. That is 4 plus 1 minus 1 divided by 3, which is the number in here of elements that you've got, minus 1. And this gives you exactly 121 elements. That is 121 words over this alphabet A, B, C, which have a length smaller or equal to 4. And you can apply the same formula to a binary alphabet where you've got only 0 and 1. And then you would see that the number of bit strings up to length 4 would be bit string 0, bit string of size 1, and so on up to bit string size 4. And then you would replace 3 to the power of 4 here by 3 to the power of 5 here by 2 to the power of 5, which is 32, minus 1 divided by 1. And that gives you 31. So you've got exactly 31 bit strings up to the length 4. And this is all the numbers that you can represent. And with this, I'm concluding this introduction to strings. It is now 3:01. Let's say we've got, let's have a slightly longer break. Let's say until 9 minutes, until 3:10. And then we will continue with the next topic, namely elementary logic. Okay. Now, let's leave these basic introductory definitions behind and continue with what is going to be our main first major topic. We will be looking at elementary logic. So, as a form of introduction, if I can have everyone's attention, please. As a matter of introduction, everyone, look at this example here. Suppose we want to say that a necessary condition for the program, just an arbitrary program, to terminate is that the user inputs a positive number. A necessary condition for it to terminate is for the user to input a positive number. Suppose you would like to verify this claim formally. Assuming that you know this symbol here, the logical implication, which of the two formulas would you use to verify and then prove the claim? Which of these two formulas does correctly represent the claim a necessary condition for the program to terminate is to get a positive number as input? Is it terminates implies positive input, or is it positive input implies terminates? What do you think? The second one? Does you suggest the first one? And indeed, yes, this is a bit of a tricky question, but it is true that intuitively the first choice might be the second one, but it is actually the first one, because it says a necessary condition for the program to terminate. And what the second one says is only that if you give it a positive input, then the program terminates, which might be just as well, but it doesn't say anything about what happens when you give it a negative number as input. It might be the case that the program also terminates when you give it a negative number. This only says when you give it a positive number, it terminates, but that doesn't exclude the case that it also terminates when you give it a negative number. But when we say a necessary condition for the program to terminate, we say that the program would not terminate if you don't give it a positive number. In other words, whenever it is the case that the program terminates, then this necessarily implies that you have given it a positive input. It's a very simple example that already shows how very careful one always has to be as a computer scientist as well as a mathematician to use precise formal ways of expressing something that is only informally described. And it might be very important when we as computer scientists talk to stakeholders, for example. They give a specification that we make absolutely clear formally what, and you agree with your stakeholder, the program should achieve. Should it be a necessary condition for it to terminate or a sufficient condition to terminate? Sufficient condition, that would be the right way. But if we say necessary condition, then this is what needs to be expressed. So we will be looking at cases like this and how to deal with this formal logic in this chapter on the introduction to elementary logic. So this would be the correct answer for this particular claim. Mathematical proofs, they also use logic. You can view a mathematical proof as when you have a proposition P, a claim that you want to prove. A mathematical proof typically is a chain of logical deductions leading to P from a base set of axioms. Here's another example. An interesting fact, theorem, proposition is that every group of 6 people always necessarily includes a group of 3 who each have met each other, or the 6 people include a group of 3 who have not met a single person in that group. In other words, if I were to take a group of random students here in this room, 6 people, then there would necessarily be 3 of you who have all individually met, or there will be 3 of you who are strangers to each other. And this is only true for 6 people. If you have 5, this would not be the case. You could have that any 3 people you take together Two would have met, but the third person might have met only one, but not the other. This is a nice fact and simple proof, or maybe not so simple, but proof that can be done step by step, is by case analysis. You just pick the first two people and then you make assumptions. Either they have met before or they have not. And then you divide your proof into these two different cases and continue to make sure that if you have considered all the cases, one of these two will always be the case. I won't be going through the whole proof, but it might be interesting for you to write it down yourself. Now the question is, when we talk about propositions and logical deductions and axioms from which we derive these claims and proofs, what do we mean by this? And also, what do we mean by a sound case analysis? And all this is questions that we will be answering in this introduction to logic. When we talk about logic, then we should always keep this diagram, or the idea behind this diagram, in mind, which actually is something that we as computer scientists always have to consider. Every time we formalize something in mathematics or in computer science, then we would have, I would appreciate if you would be listening instead of distracting everyone around you. When we, as computer scientists, we formulate any real-world property as a computer program, or as mathematicians we formulate a real-world property, then we are using symbols to represent individual aspects of the world that we want to formalize. And these symbols, they necessarily represent only part of the world, namely the part that we are interested in. In the actual world, we might have physical operations that map the world from one state into another state, whereas in a computer program or in a mathematical formalization of aspects of the real world, we would be using symbols, and we manipulate symbols. All a computer program does is manipulating symbols. And then in the end, when a computer program has calculated something, or we have derived something from our mathematical formalization, then again we interpret this as a result that should have some relationship to the world. As I said, necessarily with symbols we can only represent a small part of the world. And there is this famous quote which says that essentially any model that you build is wrong. Why is that the case? Because you will necessarily be missing something. Another famous quote is that the world itself is the only correct model of the world, and every time you build a smaller model, then you're missing something. So what is really important is that we keep this in mind, and we also keep in mind that nonetheless, even though we ignore lots of aspects, some of these models might be useful, because something that we calculate here might have a good relationship to what we are looking for in the real world. When we talk about logic, like the elementary logic, then the main relationship between symbols and the world that we want to formalize is that of a sentence of a language, in this formal language, in the logic language, the language of logic, being true in the world. We can say that when we talk about natural language, that a sentence in natural language, like English, but it could also be Cantonese or Walpiri or any other language that has a certain meaning, we can say that this is declarative, or as we call it, a proposition, if it can be meaningfully said to be either true or false. And here are a few sentences where we would all agree that we can understand them and say, yep, they are either true or they are false. Richard Nixon was president of Ecuador. The question is which Richard Nixon we are talking about, but we could say it's true or false. A square root of 16 is 4. We could also make a statement, Euclid's program, the algorithm that we have seen yesterday, gets stuck in an infinite loop if one of your inputs is 0. Is that true or false? You have to recall the algorithm and maybe try it out when you run the corresponding Python program, but it is clear that this is a statement that is either true or false. Statements that we as computer scientists are often interested in is properties about a program. For example, we might have written a sorting program that sorts numbers, and then the statement would say whatever list of numbers you give as input, it outputs the exact same list, but with all the numbers in increasing order. If your program is correct, then it would satisfy this statement. There are famous statements that in principle we can say they must be true or false, but it was very difficult and for a very long time open question whether this is actually true or false, whether this has non-trivial integer solutions for n greater than 2. We know that this is easily true for n equals 2, 3 square plus 4 square equals 5 square, but does it have solutions for n greater 2? No matter whether this is a statement that is true or false, we can safely say that we can understand it as a statement that is either true or false. Of course, we can build correct sentences in English or sentences that are not declarative sentences and not even proper English. The first one would be an example like this. This is an example of a sentence where we also wouldn't say it's a proposition. It doesn't ask us whether it's true or false. Questions are often also not propositions. It's a question, but it's not something like you want to say that the question itself is true or false. Of course, you can answer yes or no, but it doesn't mean that the question itself is a proposition. Please waive the prerequisites for this subject. For me, again, is not a proposition that you would say is true or false. When we talk about logic, we want to be talking about properties that can be expressed like this, that are meaningfully be said to be true or false. What we can do and like to do in logic is that we take some of the compositions that are being used in natural language and formulate them as logical operators. Declarative sentences in natural language they can be compound, built of other smaller sentences. And as I said, propositional logic is a formal representation of some of these constructions that we can use. And then we build we know the truth value of a compound sentence if we know the truth values of the individual sentences. For instance, lists L and M contain the same elements, is one part of the statement, and we say that list M is ordered. If the individual parts of this claim are true, then we know that this, as we call it, conjunction, both conditions together are true. We can also say something like either you have a passport or you cannot travel abroad. This would be a statement that uses the so-called disjunction. Either the first part is true or the second part of the statement is true, or maybe both are true. And we can say it is not the case that this program always halts. This adds the so-called negation to a statement. The base sentence says this program always halts, always terminates, and then we extend this by saying it is not the case that this program always terminates. These three ways of combining sentences, and, or, and not, they are most important for elementary propositional language. However, there are lots of ways of combining sentences that don't have this simple logical or truth functional interpretation. If you say something like Trump believes that Iran is developing nukes, then we have this basic statement and we extend this by something about belief. And we don't have a basic operator for this. Same with saying not only that something is true together with another statement, but that one is the reason for the other. This program always halts because it contains no loops. There is no truth functional operator. Or something that talks about one event happening after the other. The disk crashed after I saved my file. Again, doesn't correspond to a simple logical operator in propositional logic. However, I should add that in order to account for this, there have been lots of attempts and formalisms that extend classical propositional logic, which is the logic that we will be looking at, with additional operators that can be used to represent and also reason formally and logically about these and other constructions. These are known as modal logics, and they in particular talk about beliefs and knowledge. I know that something is true is different from saying something is true. I believe that something is true. Or they talk about temporal relations. P is true after Q. But we won't be looking at these modal logics, just in case you're interested in particular in those and their formalization. What we will be looking at is the standard classical propositional logic, which is built based on these three operations that we have seen in the three example sentences, the so-called conjunction, the disjunction, and the negation. The conjunction, the standard way of saying this in English, is to say and. There are other ways of saying this. You could say A is true, but B is also true, which means the same as A is true and B is true. With the but, you may want to express that it might be a bit surprising that both are true together, but logically speaking, it means the same as saying A is true and B is true. And often in English, we just combine sentences. We say A, comma B, comma C, and D, and then we mean A and B and C and D are all true. Disjunction means or. Often we say either this is true or this is true. And negation, the standard way of saying the negation in natural language would be to say not, the program does not terminate, or we say it is not the case that the program terminates. We can express the meaning of these three operators with the help of truth tables, where we say that when we can say whether the individual statements A and B are true or false, is the composition of these statements true or false? And if you have seen elementary propositional logic already, then this wouldn't come as a surprise to you that the conjunction is true only in case A is true and B is true. As soon as one of these two sub-sentences, one of these two individual propositions is false, then the conjunction would be false also. Unlike with disjunction, the only way in which a disjunction can be false is that both A and B are false. As soon as one of them is true, you would naturally say that A or B is true. For A or B to be true, it suffices that A is true, and it also suffices that B is true. And we can also have the case that is certainly not excluded by saying A is true or B is true, that both are true. For negation, I think this is also pretty clear and straightforward. If A is false, then the negation of A is true. If the program does not terminate, that is, it is false that the program terminates, then we would say it is true that the program doesn't terminate. And if the program terminates, then we would say that it is not the case that the program doesn't terminate, or the program not terminating would be false. What are possible applications of this line of reasoning? One nice and simple application of this propositional logic reasoning would be in programming statements that use conditions. For example, this statement here, again using the Python syntax for a conditional statement, is a compound statement that says that perform the following instructions only in case x is greater than 0 or x is smaller or equal to 0, but then y has to be greater than 0. And you might find this very natural to type this in because this is exactly the condition that you want to have. We can formally analyze this condition and actually from this derive that there is a simpler way of expressing exactly the same thing. Let me do this. Let me call the first definition x greater than 0, the first part of this definition p, and the second part, or part of the second part, let me call it q. That stands for y is greater than 100. Then what my condition here expresses is the same as p or not P and Q. Why is that the case? Because x smaller or equal to 0 is the negation of x greater 0. Then I can analyze the truth table for this compound formula. And I can see, for example, if both P and Q are false, then this would be false, because this part is false. Also, this is false, because this is true, but Q is false. So if x is smaller or equal to 0, which means P is false, and also y is not greater than 100, also this is false, then this condition is not true, and the following statements would not be executed. In all other cases, however, if you look at this in detail, you will see that this formula is always true. For example, if P is true and Q is false, then clearly P or not P and Q must be true. The same for the other two cases. And if you now look at this truth table and compare it what we had on the previous slide, you will see that this is actually exactly the same as the simple disjunction between P or with P and Q. So that this is equivalent to P or Q, and if we apply this conclusion from this truth table, then we will see that this condition here can actually be simplified to this. And in all possible cases, for all possible values for x and y, we can be guaranteed by this logical analysis that this condition here would do the exact same thing as this condition. That might be easy to see with an example like this, but if you have very complicated conditions, then an analysis like this might make it really possible to significantly simplify a convoluted condition that you have here, just by simple logical reasoning. Now let's have a look at one more operator, which does correspond to the implication that we had at the very beginning when I was asking this introductory question that I wanted to see. The question was, it is a necessary condition for the program to terminate that your input, that you give it a positive input. And then the question was the implication, which is the proper way of using the implication. It's not surprising that this is a bit more difficult usually than conjunction, disjunction, and negation. And you can even appreciate this from what is being said here. Suppose we have, or we want to express the fact if A then B. We also may want to express the fact that A is the case only if B is the case. Or we want to see B if, say, B if A. A implies B. It follows from A that B, we might want to say whenever A is the case, B is the case. Or, and this now goes back to the beginning, A is a sufficient condition for B. Or B is a necessary condition for A. Then all these statements may sound different, but logically speaking, they all together mean the exact same thing. And this is why implication is a bit difficult. In particular, you can see here this reversal of A and B. It is the exact same thing to say that A is a sufficient condition for B as to say B is a necessary condition for A. And why is that so? Because if you go through every individual statement, then you will see that each of these statements has the property that if the statement itself is true and A is true, then B must be true also. So if we assume that any of these statements is true, for example, B is a necessary condition for A, then if that is true, it means that when A is true, B must be true. And why is that? Because we said that it is a necessary condition. We can't have A without B. In other words, whenever A, then also B. And this is the same as this. And whenever A, then B is the same as A implies B. Here is an example which uses actual individual sentences for a compound statement like this. If you are from England, then you are from the UK. So being from England is a sufficient condition for you to be from the United Kingdom, but it's not a necessary condition. The United Kingdom might be getting smaller in the future, who knows, but it's still larger or contains more than just England. It is not a necessary condition. It's a sufficient condition, but not a necessary condition. So we don't have the implication in the other way around. And it's really very important, in particular when we use the implication, that you think about exactly what you want to express so that you can be sure what you do mathematically corresponds to what you intended to express. So what all this means is that we can at least approximate the English meaning of all these statements on the previous slide by saying that it cannot be the case that A is true and B is false. And this is the mathematical logical interpretation of this implication. A implies B has therefore the following truth table. The only way in which this can be false is that you have that A is true, but B is false. If A is true and also B is false, then you don't have that whenever A is true, B is true. But in all other cases, A implies B is true, because this, A implies B, is the same as not A and not B. And if you don't see this immediately, it might be very helpful for you to draw the truth table for this compound statement to the right here, and you will see it has exactly these entries, TTFT. Now, this is a bit more controversial, as I've said, because it's only an approximation to English. Because very often in English, when we use the expression if A, then B, we do mean that there's a causal relation. Somehow A causes B. This causal relation is lost with a truth table like this. Nonetheless, it has proved to be adequate for capturing mathematical reasoning, and it often gives us reasonably correct formalizations of what we want to express with the English sentence. What we can derive from this or take away from this is that mathematical reasoning does not need all the features of English. Very often you can get useful results even without capturing, in this particular case, this causal relation. Just take A implies B mathematically, as I said, as. It is always true, but when A is true and B is false. This would be a violation of this connection between A and B. Now let's have a look at this exercise here, the purpose of which is to try to see whether when we are given statements in natural language, whether we are able to write the correct logical formula that corresponds to exactly what we want to express. By the way, this here indicates that this is an exercise that was taken from the auxiliary textbook, the one that you can download as PDF. And if you want to look at a few exercises, then you would see this will be in this chapter. And around this exercise, you might find some exercises related to this propositional logic. Of course, there's also lots of exercises in the main textbook on propositional logic in the corresponding chapter. Now, in this problem, we have three propositions, three statements. You get a high distinction on your final exam. You do every exercise in a textbook, and you get an HD in the course itself. So there's two different HDs, one in the final exam and one overall. Now, these shall be abbreviated by P, Q, and R. And it is your task now to think about how you would translate into logical notation with the help of P, Q, and R and the logical connectives that we have seen so far to translate this into logic. So the first statement says you get an HD, you get a high distinction in the course, although you did not do every exercise in the textbook. Does anyone have a suggestion for how you would express this in logic? Anyone? P and not Q? R and not Q. Yes, this is exactly right. So we've got the A is R for you get a high distinction in the course. And also, we just ignore this although, even though that expresses a certain surprise maybe. We just say it is the case you get a high distinction, and you did not do every exercise in the book. So R and not Q would be the correct way to express this. Example C. In order to get a high distinction in the course, you must get a high distinction on the exam. Okay, so P is a necessary condition of R. P is a necessary condition of R. Can we assume that this is correct? And what would be the correct implication for this? R implies P. Yes, this is exactly right. R implies P. You get a high distinction in the course, but when someone tells you that they got a high distinction in the course, you can immediately conclude that they must have gotten a high distinction in the exam. So this is a bit tricky again, and you might intuitively think P implies R, but the way this is phrased is that you cannot get a high distinction in the course without a high distinction in the exam. So getting high distinction in the course, R, implies that you must have gotten a high distinction on the exam. Again, the implication is a bit more difficult, but yes, this is exactly right. A, C, and what's that called? D. Last example, you get a high distinction on your exam, but you don't do every exercise in this book. Nevertheless, you do get a high distinction in the course. How would you express that? P and not Q and R. So, and R, you do get a high distinction in the course. You don't do every exercise, and you get a high distinction in your exam. So here, a lot of English connections are being used, like but and nevertheless. However, if we want to translate this into logic, we would just combine these with the help of the and the conjunction. Very good. So this is exactly this is the answers that we get for these three, and again, both in this auxiliary textbook as well as in the main textbook, there are lots of other little exercises with sentences in natural language and the question to translate them, how to translate them into logic. Let's have a look at another relatively popular expression in English and how to translate this. At least one common meaning of saying A unless B is to approximate this as not B implies A. As an example, if you say or you claim that you will be going swimming unless it rains, then you make the statement that I will definitely go swimming in case it is not raining. That doesn't exclude the case that you will also be going swimming when it is raining, but you do say that I will definitely go swimming when it's not raining. The correctness of this translation might be a little easier to see if you look at this example. I do not go swimming unless the sun shines, in which case you want to say if the sun does not shine, then I don't go swimming. And this is the same translation with the help of this implication here. Do note that I go swimming unless it rains, but sometimes I swim even though it is raining. Does make sense. So when you want to translate into logic, A unless B, then this should not imply that if B is true, then you don't go swimming. or not A is the case. So this only talks about what happens not B, unless B says definitely when B is not the case, then I will do A. And this is exactly what is expressed here, but is not necessarily implying this. And indeed, you can have that this is true and that B and A is also true. Finally, we have, and this is a symbol that we have even seen earlier, which is often being used when we talk about proofs and logically so-called equivalent statements. We have the expression just in case to mean that, for example, or in general, A just in case B usually means A if and only if B. And this is written with the help of this symbol, the so-called by implication, or the implication in both directions, which stands for, as I said, logical equivalence. A if and only if B, or A just in case B. As an example, the program terminates just in case the input is a positive number, means the program terminates if and only if the input is positive. In this case, we have that positive number or positive input is both necessary as well as sufficient. So we can conclude it in both directions. We can say if the program terminates, we gave it a positive number, and if we gave it a positive number, then it terminates. Or I will go swimming just in case I won't play soccer, which can mean or should mean if I play soccer, I won't be going for a swim, and also vice versa. I will do exactly one, but not the other. That is A if and only if B, where B is this negated statement here. The truth table is a combination of the implication in both directions. So you say that A if and only if B is true whenever A and B have the same truth value. That is, they are either both false or they are both true. And this truth table is the same as saying A is a necessary or B is a necessary condition and a sufficient condition for A. So it's the same as A implies B and also B implies A. And again, you're invited to, if you don't see that immediately, add the truth table for this conjunction here. You will see that you will obtain exactly the same T, F, F, T for these 4 rows. Let's come back to the formal language introduction earlier today, because now we can say that what do we mean by propositional logic as a formal language? How can we write down everything that we have written down informally so far, like these here? All these are syntactically valid formulas in propositional logic. What would not be syntactically valid would be to say something like R implies P not. This uses correct symbols, but it doesn't have a correct meaning. R implies P not is not understandable. It's not the correct sentence. This is exactly what this slide here tells us. It tells us that when we want to define what we can express syntactically correctly in propositional logic, we assume that we have a set of propositions like P, Q, and R. And on the basis of these, we use this alphabet for propositional logic. We take all the logical connectives that we have seen so far, plus we may want to take parentheses in order to express preferences. For example, here I've used these parentheses to make clear that this is one subformula and this is the other subformula. And sometimes we even want to use these very specific formulas here. This stands for always true. This stands for always false. This is our language. And then we can define what are meaningful words over this language, what are correct ways of using this language. In other words, what are formulae of propositional logic? This is defined as the smallest set of words that satisfy this recursive definition here. It says that always true and always false are correct formulas. All propositions themselves, like P, Q, R, they themselves are formulas. And then we can combine these individual formulas with the help of our connectives. If phi is a formula, then we can always put a negation in front. And if we have two formulae, phi and psi, then we can say phi and psi, phi or psi, and also the implication and the by implication, including these parentheses here. So by definition, I would always use parentheses around a connective and its two arguments. But the convention is that we often drop parentheses when there is no ambiguity. And in this case, the standard assumption is that not binds more tightly than conjunction and disjunction, which in turn bind more tightly than implication and by implication. By which I mean that, for instance, here, I didn't use parentheses in order to say that I mean not Q. I could have put parentheses around here, but intuitively I have omitted this. But it is very clear that this is very different from saying not Q and R. And indeed, this would have a different truth value from not Q and R. So parentheses can be very useful, but we may not always have to use them. In which case, when I, for instance, have P implies Q or R, by convention, according to the slide, the disjunction binds more strongly, and therefore this should be read like this. Right, so that does conclude everything that I wanted to introduce in this first week. Let me mention that in the textbook, there's not only exercises for every individual chapter, but there's also for every individual section of the chapter. But there's always also a last chapter with exercises that somehow combine everything that has been talked about in the previous sections. These are called supplementary exercises in an extra section at the end of every chapter. And I've picked these two here, which I don't think I've got time to go through, but it might be a nice idea for you to try to solve them yourself without looking at the next slide where there is the solution. And generally, you can go to this supplementary, or this section with supplementary exercises and look at a few others. You may see that you can't solve all of them based on what I've taught, because I won't be covering everything in a particular chapter. So jumping over the solution, let me remind you that there is the first problem set for this week, your homework, that you should do the homework before you do the quiz as assessment for the homework. I've said that the first quiz is just practice. It doesn't count for your final mark, but it's still certainly a very good idea for you to familiarize yourself with the environment. Do the practice quiz before the deadline next Thursday at 10 a.m. And if for the last minute I can have everyone's attention, please keep in mind the following quiz rules, including this week, even though it's only practice, but in particular for all the other weeks. When you go to the quiz, try to use your own best judgment to understand and solve a question. Even if you're not entirely clear how to interpret it, just try your best possible understanding. If you do believe that something on Moodle is really obviously wrong, then please don't use the course forum to post your question, but email me. Now, we've tested all this. This shouldn't happen, but if you think something is really seriously wrong, then please do email me instead of posting it on the course forum. You're most welcome to discuss quizzes on the forum, but please do this only after the Thursday deadline. Do not post specific questions about the quiz before the deadline. Also, it makes little sense to ask me to check your answers before you submit them. That would be like sitting in an exam and before you hand it in, asking your invigilator if everything is correct. And also don't agonize too much about a question that you find too difficult. Just 10 seconds. The reason for this is that the homework and the quizzes are for you to demonstrate your ability to understand and solve problems, like an exam. So you should take it as even a mini exam every week.